This is somewhat related to the natural capital accounting material that we had just come out of. We just talked about how mineral stocks, groundwater stocks, soil resources, those things are natural capital. Those are natural capital assets, which contribute to the wealth of a society. They contribute to the production capacity of a society. We looked at an example of groundwater where there's maybe you have some farmland which benefits from the fact that there is some groundwater sitting below your land, and so you're able to put down a straw and suck some of that out, and then you can irrigate your crops. That aquifer example was a similar kind of resource to a non-renewable resource. It renews, but it renews typically much slower than it can be harvested or pumped. So groundwater, soil, those are both assets which have some non-renewable characteristics. They're not completely non-renewable. Soil does regenerate over long time scales. Aquifers do recharge over time, through rainfall and then gradual seepage down back into the aquifer. But on short-term scales, those things are kind of non-renewable resources. And so we looked at an example last class of a study from Kansas that was trying to determine what was the wealth that was stored in this groundwater aquifer underneath the cornfields of Kansas. How did we monetize that? Because if you remember, those assets eventually, those groundwater assets, those aquifers, eventually, if you pump them too fast, they run out, and they produce a lot of value in terms of the irrigation that they can supply to crops, and so they enhance crop productivity. They increase the capacity to produce crops, and so if you conserve that has value in terms of the wealth that you're saving up for the future. If you pump it, you're able to produce a lot now, but you sort of forego production possibilities down the line, and so we kind of frame that as in our discussion of natural capital accounting. If these groundwater resources are not monetized in any way, then you have no way of kind of gauging how well you're doing in terms of your overall well-being of your society. Maybe you're producing a lot of crops, but you're drawing down your groundwater stock. Your groundwater stock is perhaps falling precipitously. That's making you worse off for the future. But if your accounting system doesn't account for the fact that those resources are being drawn down, then it can appear like you're having lots of economic growth, but you're not seeing the hidden costs of that. And so we're talking about how it's important to be able to account for those, bring those into national income accounts in order to show the value of those resources and to incentivize conservation or allow for there to be some kind of policy case for conservation, given that those things have value. So that was kind of where we came out of, and this leads us nicely into this discussion of non-renewable resources, where we're thinking about things that don't replenish naturally, they don't grow, they're not organic resources which have some kind of growth function. They're not fish, they're not forests. So these non-renewable resources are things like minerals, coal, petroleum, other kinds of fossil fuels that are stored in the ground. And so our analysis of those kinds of things, those metals and hydrocarbons, those are what we're going to be talking about next. So these are fixed. I want to actually show, however, an interesting graph. This is from the textbook. This is from Harrison Roach, the 4th edition of your textbook. And I just mentioned how the planet has a fixed stock of these non-renewable resources, these hydrocarbons or these minerals. In this case, we have 3 different kinds of metals. We have lead, we have zinc, we have copper. And this graph, this y-axis of this graph, represents the global economic reserves of these metals. So these are the amounts of the metals in the Earth's crust that we can access with existing processes and technology. Remember, we have population. Population has been growing over this time. We have 1996 on this left-hand side. We have 2016 on the right-hand side. We added something like roughly 2 billion people to the planet between 1996 and 2016, maybe 1.5 billion, might not be exactly 2 billion. How is it the case that we have reserves of these non-renewable resources growing over time?
Is it maybe technological innovation is making them easier to extract?
Yeah, you're on the right track. Why is it the case that that wouldn't just why wouldn't that just lead to faster depletion of the resource? Why are these things still going up even though we have better capacities?
Yeah, I don't know. Maybe they're discovering more. I don't have a handle on it.
Yeah. That's much closer to the reason. Yeah. So you said technological progress makes it easier to extract. The fact that the technology is changing means that things which were previously inaccessible to us are suddenly now accessible. And so, like, yeah, the effective access to those minerals are changing with that technology. That's more precisely what the reason is for the growth in the stocks. Yeah. So yeah, this kind of just brings up a very important distinction between types of resources. So we have a fixed stock. We literally have a fixed stock. Um, the Earth doesn't add very much material. We get some meteors that come in from space and strike the Earth. So there's a little bit of transfer of mass between the Earth and space and the rest of the universe, but most of it is just contained inside the rock that is the Earth. But there's a difference between physical supply and economic supply, and this is critical for thinking about the economics of non-renewable resources. Like I said, the planet is a single piece of rock. It's self-contained, but in a way there's like a separate world, a little bit different from the physical world, which is like the economic world, the supplies of these resources, which sort of represent what human beings can use these resources for, the ways that we can access them, the ways that we can transform them into other useful things, the ways that we can discover more. There's like another whole other separate economic life that these resources and this planet has, which is distinct from just the physical and chemical properties of the Earth. So this distinction between physical supply and economic supply is critical for understanding kind of what's going on this previous graph, where we have some growth in the reserves over time. So just to formally define these things, physical reserves are the total amount that exists in the Earth's crust. It's finite, but the economic reserves are a little bit of a different thing. Those are the known reserves, the reserves that we've identified, that we can extract profitably based on the current prices and technology. And both those things are important. Both the current prices and current technology are both extremely important for determining kind of what these reserves are, how large they are, and how long we might expect them to last. Sarah, you had mentioned that we have technology that can develop and advance, and that can lead to an expansion of the effective reserves that we have access to. I guess the next question I have is it possible that reserves can change even without a change in technology?
If there's a change in the profitability of the reserve, potentially.
Yeah, exactly. Yeah, so that's, if you think about the ground, we have this, maybe the surface of the ground that's here. We have some stocks of minerals, and some of them are deeper in the earth. Some of them are shallower. And so you might imagine maybe it's like $10 per pound to extract the minerals that are sort of at this level in the Earth's crust that's closer to the surface. Maybe that's $10 per pound to extract and dig those up. Maybe these minerals down here, maybe these are $20 per pound. So you can imagine, let's say if the price of minerals, if the price of these minerals, whatever these are, if it's currently $18 per pound that these minerals can fetch on the open market, the reserves that are closer to the surface, maybe we know about both of these reserves. Maybe we know that these blue reserves exist, but they're currently $20 per pound. Those would not be economic reserves at $18 per pound. But let's say if some time goes by, and all of a sudden there's higher demand for these resources, or other supplies elsewhere which are getting scarcer, and so in general these resources are getting scarcer. Maybe there's an increase in the price from to $25 per pound, and then all of a sudden these deeper reserves become, they sort of transition, they sort of get recategorized from non-economic reserves to economic reserves as a result of the change in price. So that's another key point I want to emphasize here, which was sort of hinted at this previous slide. Economic reserves are the reserves that can be extracted profitably based on the current prices and technology. So technology is important, but also the prices. Even if technology is fixed, if the price goes up, reserves which were previously non-economic can suddenly become economic. So we can think about the different things that can lead to economic reserves going up or down. So the simplest thing here is if we have extraction, that's going to be something which can diminish the economic reserves. If we take those minerals out of the ground and put them to use somewhere else, they're no longer part of our reserves. They're now, they're in the consumer products that we buy. So those reserves fall as extraction happens. But then there's other things that can be changing at the same time, which could affect the economic reserves. So new discovery, we could actually just by going out and drilling more test wells to find whether or not there's actual identifiable petroleum in a certain area. Just by going out and doing some testing, doing some geological tests, we could actually increase our economic reserves, or increase the reserves that we've identified, which we could potentially extract. That's just an information thing. That's just like your reserves can increase just by having more information about where things are and whether there are stocks located in a particular area. So discovery can happen. Resource prices, I have a plus sign here indicating that that's something that could increase economic reserves. That is true that it could increase economic reserves. That would be similar to the case that we just saw, where these $20 per pound reserves become economic after the price increase. But this actually could also be something that negatively affects it as well. If the price falls, if the price actually goes in a different direction, maybe the price plummets. Instead of going from $18 to $25, maybe it goes in reverse, and all of a sudden it becomes $9 per pound, and then all of a sudden you have sort of a decrease in economic reserves, because now neither of these stocks, neither the $20 per pound stock nor the $10 per pound stock, are economically extractable at $9 per pound. And so that's something, just to be sort of more complete about it, for this resource prices factor, that's something that could either be positive or negative in terms of expanding or contracting the economic reserves. And then technology is also going to be a factor. So you could have prices being constant, but you can have innovations which can expand. Typically that's only going to be expanding the amount that's available. You're not really going to get a technological advancement that makes it harder to get them out of the ground. That's pretty much by definition. So this one is pretty much just going to be something that expands it. So, we're extracting, we're taking things out of the ground, we're taking minerals out of the ground, we're taking non-renewable hydrocarbons out of the ground. But at the same time, we're also discovering new ones. Prices are changing, and technology is advancing, and all those things are changing all at once. And that's kind of how we can get this kind of weird situation where, even though we have many more people and much more demand and many more uses for these things, many more final uses for these kinds of minerals, the reserves can change based on some of those things that are going on behind the scenes, both with technology developments, discoveries, and with price changes. I guess the question is, sort of the question that motivates this next slide is, how much do we have left? that's kind of the point. That's sort of ultimately the point of why we study natural resource economics and we study non-renewable resources is really fundamentally about getting at this question of how much do we have left. One way of measuring that is you can think about something called the static reserve index. That's composed of two parts: the economic supply and annual consumption, and you take you divide economic supply by annual consumption, and that gives you some idea of the number of how many years do we have left of a particular resource. We know how much there is, that's the economic supply, or at least we know how much there is in terms of what we can extract profitably at current prices and technology. That's the economic supply. And then we know kind of what our rate of consumption is, and we divide the supply by the annual consumption to sort of get the time left before those things run out. So in a sense, this tells you something about how much time we have left for some of these resources. But in another way, it doesn't. It actually the more I think about this, the less I'm actually convinced that this static reserve index tells us anything useful about natural resources and non-renewable resources. Because notice here that the economic supply and the annual consumption are both very flexible. They're both very responsive. They're not rigid. These are not like, it's not like planets in an orbit, around the sun. There's a gravitational pull on those objects, and you can predict exactly where they're going to be 30 years from now, because they're going to move according to Newton's laws of physics. That's a very rigid system. This is completely the opposite. This is not a rigid system at all. This is a very flexible system. This is a system where there's constant adjustments to scarcity. There's constant pushes to get more resources when things are scarce, as well as on the demand side, when things are scarce and prices are high, there's constant adjustments to trying to find ways of using less materials. I have a couple interesting stories that kind of go along that sort of illustrate how just the kinds of different adjustments that we can make when materials get scarcer. And so the first example is railroad cars, which are huge, 30 tons of metal, these huge cars that help you ship freight on railroads around the country. It's an interesting coordination problem where you're trying to figure out how do I make the best use of my railroad cars, given that I have certain things I need to transport from one place to another, and maybe my cars aren't in the right spot, so I have to get my railroad cars to where they need to be. So there's materials that are required for these railroad cars, but there's a lot of them that actually are just sitting there not doing anything much of the time. There's a lot of these railroad cars that are just sitting in the depot and not actually being utilized. Maybe 5% of your railroad cars, if you're managing a stock of railroad cars, you're managing a freight company, 5% of those cars might be utilized over time, and the other 95% are just sitting there, sitting idle because you haven't optimized your system well. Over time, over the the last several decades, the utilization rate on these railroad cars has increased, not that much, but from 5% to 10%. So we're sort of that's like the fraction of time that a given railroad car is being utilized. It's actually carrying some freight. What this has allowed us to do is actually we don't need as many railroad cars, and so that metal or those materials can go towards something else. Can either that metal can be melted down for scrap and used towards something else, or you just don't need to construct as many new ones. So this is like just one of the possible ways that we can use resources more efficiently and actually use less of everything, which is just to optimize the existing stock that we already have. This is a small increase in efficiency from 5% utilization to 10% utilization, but that difference from 5% to 10% means that you actually only need half as many railroad cars as you did before. And so the metal that's required to construct those can be used for something else. So you can kind of, in effect, you can cut in half the amount of metal that you actually need for railroad cars by just doing something like optimizing your logistical system. That's just one example. There's another example, which is the fact that aluminum cans. So back in 1960, when the first aluminum cans were being used for beverages, for beer and soda, 1960 we had 85 grams per can. 1972, 21 grams per can. 1988, this had fallen to 16 grams. By 98, this had fallen to 13.6. As of 2011, we were down to about 12.75. All right, so this is just these two, this railroad car example. The railroad cars is one example of the ways that just by optimizing our system a little bit better, we can get away with using fewer resources. So there's opportunities to sort of squeeze more out of the resources we already have. There's a lot of slack in the system to be able to squeeze more value, more use out of the resources that we already have by optimizing our railroad cars. That's kind of one anecdote that sort of illustrates that point. And then this aluminum can example is another where these producers, Coors and Budweiser and Miller, this aluminum is it's a cost to them. They have to acquire the aluminum. They have to acquire those resources and use those as inputs into selling their product. And they don't want to have to buy more aluminum than they actually have to. So their sort of pursuit of profit, their pursuit of trying to minimize costs and provide a product that doesn't require as many resources, this has led to this drastic sort of decline in the amount of materials that are required to produce a single aluminum can. And it's really interesting the ways that technology has allowed this to happen. As part of this the development of like 3D imaging software where you can run experiments on materials just with a computer simulator. We can use computers to very precisely design the cans with exactly the right shape that will be sort of as strong as possible while using the fewest materials as possible. All these kinds of innovations in software and computers and lasers, and then the actual machines that manufacture these cans. All this development has led to a decline. It's about 15 or 20% of the material that we used to need to produce a single can. We only need about 15% or 20% of that today in order to produce the same product, and even perhaps a better product that's even stronger and more durable. So that's just to say there's all kinds of different innovations and different margins for substitution, different margins for using resources more effectively as they get scarce, and all these kinds of things are happening. No one's in charge of this process. No one is directing this process. Nobody is making sure that the amount of aluminum in the cans is falling over time. This is happening because companies are interested in not having to pay more for producing something than they actually have to. That's the case with railroad companies and freight companies, and it's also the case with beer manufacturers and soda manufacturers as well. So that's just a little bit of some real world examples of how, if you imagine, if let's say we have what might look like a scarcity of aluminum, you better believe that companies are going to be finding alternative ways of producing the products that they sell, and we can expect that there's going to be searches. There's going to be a hot pursuit of different kinds of substitutions that could happen, either using less of the same thing, or maybe substituting away from one kind of material or one kind of distribution process. You might substitute away from that to some other kind of process in order to try to get more from less. So that's kind of some of the things that I find most exciting about this topic of non-renewable resource use. This is a little bit just kind of a more bland kind of diagram, but this is kind of a diagram to help you think about that classification of resources that I had mentioned, where the distinction between physical supply and economic supply. There's sort of two different dimensions that are important. One is the level of geological certainty that's along this x-axis, And then this y-axis is economic feasibility. I want to just make sure that that's readable on your screens. So up in the upper left-hand corner, we have reserves that we're very confident exist, and we also are able to extract them at current prices and technology. So these are, when we think about the stocks of reserves in a country, that's what we mean. We mean reserves that are clearly identified and also very, very easy for us to obtain. All right, and then we have, maybe there's other ones which are, we haven't exactly, we don't know, maybe we don't know exactly how deep it goes. Maybe we know that there's like a stock of resources, that we're sure that it goes down to this depth, and it's possible, it's very possible, just based on what we know about geology, that it's very likely that it goes down maybe a little bit further, but we just have a little bit less confidence in how much farther it goes down. We might consider this gray area to be the inferred reserves, which we have a pretty high, maybe not as high confidence as the black portion, but we're still pretty confident those exist. That's in terms of what we physically know about. And then there's also reserves that we haven't discovered yet, which we imagine that there's probably other reserves in other parts of land that we haven't looked as carefully in, which we haven't identified, or we can't really directly infer, but we think that there could be stuff in other parts of the globe that we haven't thoroughly investigated yet. So those are reserves and inferred reserves. And then even for reserves that we've demonstrated that are there, some of them might not be obtainable given the current prices. They're just too deep, or they're the ores are too it's mixed together with too many other kinds of things, that to actually get out the valuable material that we want, it would take too much of an intense process to actually do that. So those would be sub-economic. And then these other ones would be sub-economic reserves that we don't we're not as confident exist, but we think might exist. So there's different classifications, and the United States Geological Survey has different categories that it puts these things in. But in general, we're thinking about geological certainty being one dimension of a resource, and then economic feasibility of extraction is the other dimension. Okay.